Sorry. Can you repeat again? Is there
any requirement to choose lambda 8 generator?
Okay. Understand.
Yeah. It is also a combination of the other two generators?
No, there is no condition at all. I mean, it should be linearly independent. That is the main thing. So SU3 is 8-dimensional. SU3 Algebra is 8-dimensional. So so there must be 8 linearly independent generators, right? And then any other generator you can write it as linear combination of the 8. So there is no other restriction apart from the requirement that it should be linearly independent. Okay? That's all. Then it's a matter of your convenience. I mean, sometimes it's convenient to choose some basis, sometimes it is more convenient to choose another basis, but there is no kind of deep reason for choosing one basis to another basis. There is no theoretical reason for that.
Okay. Also, are these 8 generators represent the quark transition from U to A or B, something like that?
So again, I couldn't hear the whole sentence. What was it again?
Are these 8 generators represent a quark transition? For example, U quark to D quark or C quark, S quark, something like that?
Well, not quite. I mean, that we will see. I didn't mention why Gell-Mann considered the SU3. See, this is before. I mean, Gell-Mann. This was a long time back. I mean, I don't remember the exact dates, but I believe it was in the 1950s. 1950s or so, or maybe early 60s, that Gell-Mann came out with this idea that at that time they didn't know about quarks because the QCD was still not. It was not there. That didn't exist. So what he did, what they knew was mesons. They experimentally knew that there are certain types of mesons. So the K mesons, pi mesons, eta mesons, and so on. Right. Then he found that even though their masses are not the same, but they're close enough. So he kind of assumed that, let's assume that there is a symmetry which mixes the pi mesons and the k mesons and the eta meson and so on. Right? And it turned out that there are 3 pi mesons, pi plus, pi 0 and pi minus. Pi plus is a positive charge, pi minus is a negative charge, and pi 0 is neutral. And there are k mesons, there is a k plus and a k minus, and 2 neutral k's, k0. So k0, I think usually people call it k0 and k0 bar for some reason. I mean, just a matter. Mainly there are 2 neutral k, and finally there is 1 eta. So all of them, altogether there were 8 mesons. So he thought, okay, why not put them as an SU3 octet? I mean, a joint representation. A joint representation is 8-dimensional. No? So that's how it started. But then later on, somehow his history took a completely different turn when QCD came. So in QCD, there is SU3, but that SU3 has nothing to do with the flavor symmetry. These are called flavor symmetries. So when you say U, D, S, etc., these are different quarks, and this is like U, D, S, C, etc. There are top, bottom, there are several quarks. No? But when we talk about SU3, it is another thing. It is a color. So meaning each of them, U, D, C, all of these quarks are transforming. So U, actually there are 3 U's, 3 D's, and these 3 U's transform in SU3. SU3 fundamental representation. And that is what is called the color. So QCD is based on that. The entire now strong interactions basically governed by this SU3 gauge group, SU3 interactions. On top of it, there is flavor symmetry. The flavor symmetry is what you were mentioning. Those are, of course, approximate symmetries because, first of all, not all the quarks have the same masses. The quarks have different masses. But if you suppose you say to the first approximation, to the 0th order approximation, I will assume that they all have the same mass. Okay. Then there is an approximate symmetry, flavor symmetry. So Gell-Mann was more thinking in terms of flavor symmetry. Even though at that time quarks were not known, but they knew the bound states of quarks. Mesons are basically quark, anti-quark bound states. No? Yeah. All right, so where were we actually? So yeah, this is a good point. I mean, we choose a basis, but there is nothing sacred about that basis. You could choose some other basis. Okay. It's just a matter of convenience. I mean, we find something more convenient, something else not so convenient. So the basis, so we said lambda 1 up to lambda 8 was a basis. They were linearly independent. You could not, I mean, if you say that, let's say AI is lambda I, summed over I, where AI is any number, AI are any numbers. So that's the meaning of linear independence. So you say, you look at this equation, AI lambda I equal to 0, okay? Then you can prove, I mean, with some work, you'll have to check, that the only solution to this equation is all the AI are 0. That's the only solution, okay? That means that these are linearly independent. If by mistake, suppose you had chosen some other basis, say lambda prime I, and they happen to be not linearly independent, okay? In that case, you will find a solution to this equation with not all AI equal to 0. So some AIs are not 0. That's a definition of linear independence or linear independent. Okay. So yeah, whenever you choose a basis, you should make sure that they are linearly independent, which means the only solution to this equation is all AI is 0.
It could be a similarity transformation, and also the basis maybe not linear.
You can choose a, yeah. Similarity transformation, though, I mean, one has to be a little careful because we said these are Hermitian matrices, right? In general, if you make a similarity transformation, it will not be Hermitian anymore. No. Unitary transformations you can make. Yeah.
So if we change the basis, the commutation relation and the trace relation also will not be such.
The structure constants will be different. So you see, we had some, so lambda I, lambda j, I think what we were calling it last time.
Over 2 is equal to I.
Okay, we see, yeah. Over 2, so over 2 was equal to I, Fij k, lambda k over 2. Now if you choose a different basis, these are going to change. I mean, for example, let's suppose I choose a new basis, lambda prime i's, which were given by some combinations, Fij, lambda j. These are numbers, summed over j. These are just numbers, Fij. So j, this summed over j, but I is just that, I mean, different lambda prime i's will have different coefficients, no? In this expansion. So if you do that, clearly this, sorry, don't let me not use the same F, something else, I don't know, let's call it S. Sij. I mean, F I have already used for this. So then you see, then if you look at lambda prime I, lambda prime j, okay, by 2 commutator, well, that's the same as Fi, say, L, Fj, say, R, lambda L, lambda R by 2 commutator. No? Again, summed over, L and R are summed over. And now you see, if you use that equation, not F, again, S, S. Sij, Sil, I'm just using that, Sjr times it. Then this will be summed over Lr, Sil, Sjr, and then you get here Fl, okay, I by 2, Fl, R, T, let's say, lambda t by 2. But then lambda t is, you have to again write it back in terms of lambda prime. So you have to invert this equation. And inverse exists because, we are saying this is a basis. So therefore I can re-express lambda as a linear combination of them, right? So then you see, now the new f's are pretty complicated compared to the previous one, right?
But it is not necessarily to be also anti-symmetric, right? It is not necessarily to be...
It will not be necessarily yeah, exactly. It will be certainly anti-symmetric in these two indices, ij, because clearly, if I, but not totally anti-symmetric, no. I think that even, if you just had changed the normalization of, no?
Exactly.
Yeah.
I think that's why you put the condition in the first place, the trace condition, so that we can...
Yeah, if for example in lambda 8, you had removed the root 3, no? Then this will not be totally anti-symmetric.
Professor, if we, for example, in the SU2 case, we chose, like for convenience, the Cartan's element and the positive and negative groups, and each of the algebra elements could be expressed as a complex linear combination of these three elements.
Yes.
Are those three also kind of a basis, or not because they are not part of
No, you can choose it, but except that you're complexifying, no? Because now you have to multiply by complex numbers, right? So in fact, we will see when we discuss more general discussion, not SU2, SU3, but beyond that. After this, so from next week, I'll be discussing completely general algebras. So no particular reference to any particular algebra, but just general properties of the algebra. General properties are what? There's a commutation relation. That commutation relation satisfies Jacobi identity. Things like that. Those are some general conditions. So just using general conditions, we will do this, and you will see that again when you want to study the representations, including the adjoint representation, it is much better to first complexify the algebra, which means you allow complex numbers to multiply. No? But at the end, after doing all that, then you have to restrict yourself again. So you learn the properties after complexification, but at the end you have to go back to your real things. Yeah, it's actually very convenient to complexify. Just like in SU2 you saw, writing it as j plus j minus, it was simplifying the life so much, right? Okay. So now, so let us write down the. So structure constants are given. You can of course work it out once those bases are given. These are Gelman bases. Gelman bases. Just to, I will be also I will use another basis which is more convenient for something. No, okay. So I remember lambda 8. Lambda 8 is the one which was a bit looking ugly because it was 1 over root 3. 1 minus 2. Everything else 0. That was lambda 8. And then we said that if you subtract or add, so whereas lambda 1 was 1 minus 1, 0, 0, everything else 0. Yeah? So if you choose some combinations, so choose a combination lambda, say lambda 8, say root 3 lambda 8, so that this guy is just that. And if you subtract minus lambda 1, subtract lambda 1, then this coefficient becomes 0, right? And the top guy, this cancels. And then you see the matrix becomes, so 1, minus 1, so 2. So let me divide by 2 also. So then this becomes 0, 0, 0, 0, 0, 1, 0. And then finally here, this is minus 2 divided by 2, so it's minus 1. Sometimes this looks convenient because now you see this looks like exactly sigma 3. No? So many times we will use this kind of a basis. So instead of lambda 8, we choose this basis. But of course, then it will not be true. It will no longer be true that lambda A, lambda B trace of lambda B, lambda is proportional to delta AB. This will not be anymore. If you have chosen this as your new lambda A, lambda 8, then it will not be true. But it really doesn't matter so much. This is not so important, this condition. If you satisfy this condition, trace lambda A, lambda B equal to proportional delta AB, then we'll see proportional to delta AB. Then we'll see that one can draw very nice pictures. I will hopefully by the end today I will try to draw the pictures of the roots. The pictures come out very, very nice. If you do not do that, the pictures come out a bit ugly, but the content is the same. Obviously there's no content, change in the content, no? Because this is choosing a different basis, not a big deal. Okay, so let us look at this structure more carefully. So of this lambda, so you remember what we did for SU2. SU2, what we did, we first looked at what we call Cartan subalgebra. Again, I have not defined this properly. I have not defined in a precise way, but all the precise definitions will be when we discuss the general Lie algebras. So for the moment, it's not so precise. Cartan subalgebra. So it is what? It is a subalgebra. So this is a subalgebra. Is a maximally is A. No? So it's not a unique. You could choose many different choices. You can make many different choices for Cartan subalgebra. But just choose any one of them. A maximum abelian subalgebra. Of the full algebra, or whatever the full algebra is. Of the full. So SU3 in this case. So it's a subalgebra, of course, which means that the commutator of the two elements are inside the commutator of any two elements inside here in the subalgebra should be again contained in the subalgebra. But in fact, in this case, it's also more trivial because it's abelian. So therefore, all the commutators must be 0 here, right? So or any two, if x and y belong to the Cartan subalgebra, I just write subalgebra. And then xy, so for all xy belonging to Cartan subalgebra, xy must be 0. This comes because, if I had not input this word abelian, then it should be that this should also belong to the Cartan subalgebra. Right? That is the definition of subalgebra. But now we are saying more. We are saying abelian. So abelian means that this must be 0 actually. This must be 0. Of course, 0 is an element of the Cartan. 0 is a trivial element of any algebra, right? Because it's a vector space. So in the vector space, there's always a 0 vector. All these algebras are, first of all, vector space and plus a commutation relation. So already when you talk about vector space, there's always a 0 vector. Right? So that's xy. So that's that. So now, we can, since we have explicitly we have all these matrices, we can immediately try to see what are the maximum possible choice we can make, of the maximum possible commuting things. Well, I can choose lambda 1 and lambda 8, for example. Right? These were the only two do you have in front of you that Gell-Mann matrices? Yes. Because if I write, or maybe I could just write somewhere and then not disturb it. So let me just write it down. So I will write not big lambda 1 equal to 1 minus 1, 0, 0, 0. Lambda 2 was 0, 1, 0, 1, 0, 0. Oh, maybe the other way around. Was it lambda 1? No, it was lambda 1. Sorry, it is not lambda 1. What I was writing lambda 1 was lambda 3, in fact, right? Okay. So lambda 1, so this is, okay, lambda 1 was that. Lambda 2 is minus I, 0, 0, 0. Lambda 3 was this one, 1 minus 1. Lambda 4 was 0, 0, 0, 1, 0, 0, 0, 1, 0. Lambda 5 is 0, 0, minus I, 0, 0, 0, 0, 0. Lambda 6 was 0, 0, 0, 0, 0, 1, 0, 0, 7. And finally, lambda 8, which is this one. 1 over root 3, 1 minus 2. Okay. So this I will try not to erase it. Okay. So given this 8 basis elements, so we can try to see what is a Cartan subalgebra. So if I, for example, take the diagonal matrices, there are 2 diagonal matrices, lambda 3, so diagonal ones here are lambda 3 and lambda 8. These are purely diagonal. And since they are diagonal matrices, they obviously commute with each other, right? So if I take this subalgebra generated by lambda 3 and lambda 8, this will be certainly a abelian subalgebra, right? So this is a two-dimensional subalgebra. This is generated by that. So that this subalgebra will be, arbitrary element will be A lambda 3 plus B lambda 8, where A and B are arbitrary numbers. A, B are arbitrary real numbers. Real because we want to maintain hermiticity, Hermitian condition, right? So we can't put, I mean, these are already Hermitian. All these matrices are Hermitian matrices. So these numbers that I multiply must be real. Okay, so this is a two-dimensional subalgebra, certainly, and it's also abelian because they commute. And now the question is it the maximum? Now the question is it the maximum? We could see, we can see that, for example, I couldn't add lambda 1 or lambda 2 because that doesn't commute with lambda 3. No? In particular, it doesn't commute with lambda 3. It commutes with lambda 8, but it does not commute with lambda 3. So therefore, these are not, once I have taken this as my subalgebra, then I cannot add any lambda 1 or lambda 2 into this set because then it will no longer be abelian, right? So that's not possible. Similarly, if you look at these two guys, lambda 4 and lambda 5, that will commute with the one combination of lambda 1 and lambda 8. So let me write down those two combinations. Root 3, lambda 8 minus plus lambda 3, 1/2. These are one of them for the, say, the minus sign, we already said it is 0, 0, 0, 0, 1, 0, 0, 0, minus 1. And if you take the plus sign, minus lambda 3, plus lambda 3. In that case, in that case it will be the other way around. It will be 1, 0, 0, 0, 0, 0, 0, 0, minus 1. Right? So all of these are part of the subalgebra because we are saying that I can take any number, no? Any number, multiply that, and add that. That will be also part of an element of the subalgebra. So these two are certainly elements of the subalgebra, right? Because this is just a real combination of lambda 8 and lambda 3. So, and now you see that this guy, for example, this combination does not commute with lambda 6 and lambda 7. Right? Because you see this lower block, if you look at lower block, this is sigma 3, that is sigma 1, that is sigma 2. So certainly sigma 3 will not commute with sigma 1 and sigma 2. So that's not possible. And if you now look at the remaining guys, lambda 4 and lambda 5, then look at this combination, right? So you see if you have removed these are all zeros, so that's not important. Now look at the remaining block, it's a sigma 3 here, again, right? And here again, it's sigma 2 if you remove this block, and also if you remove that, it's sigma 1. There is sigma 1. So these don't commute. Right? So the conclusion is that none of the others, no other combination of these remaining 6 generators can commute with this. So I cannot add any more generator here. This is a maximum. So this proves that it's a maximum. So this is a, we don't have a notation for Cartan subalgebra. We don't have a notation. All these notations come in the general discussion where we start defining general algebras. So anyway, the Cartan subalgebra is just this, because it's a maximal. This is a maximal commuting subalgebra. Yeah. I mean, so the conclusion is that if I look at this subalgebra generated by these two, this is in fact a maximal, and that's important, maximal abelian. Both these terms, both these words are very important. It should be abelian and maximal. Okay. So this is the Cartan subalgebra. This is a Cartan subalgebra. You could have chosen some other basic, some other elements. Then it would not be, it would be different. But okay, this is convenient because, why is it convenient? Because we already know, I mean, in SU2, what did we do? Cartan subalgebra, we just was generated by sigma 3. Right? It was convenient. I mean, I could have chosen sigma 1 or sigma 2. No, doesn't matter. But sigma 3 was convenient because it was already diagonal. Right? And because after the next step was we were looking for eigenvalues. No? But since it's already diagonal, that was pretty easy to work out. Right? So that was the idea. So we just take this lambda 3 and lambda 8. So, the generators of Cartan subalgebra. Okay. Okay. Then the next step, so that was the first step, Cartan subalgebra. Next step was to look at the remaining guys, all the remaining objects, and try to find combinations of raising and lowering. Right? But to do that, of course, now I have to complexify. Right? Because remember, also already in SU2, what we did was we had a sigma plus and sigma minus. Okay? So I remind you in SU2 what we did, we had a sigma 3, we chose it to be the Cartan. It was a one-dimensional Cartan, so it's generated by sigma 3. And then we found that the eigenvalues were, I mean, this was giving some number times sigma plus minus, where sigma plus minus was sigma 1 plus minus I sigma 2. Right? So now you see this is not real now, right? So this is not part of your Lie algebra, right? So you have to actually complexify it. So you are allowing now complex numbers to multiply. But at the end, after doing all that, after using all this, use this to raise and lower and so on, at the end we again project back to the SU2, right? Because we defined that, yeah, I mean, you can invert the relation. Sigma 1 is sigma plus sigma minus by 2, and sigma 2 is sigma 1 minus sigma plus minus sigma minus divided by 2i. So you find back this combination, and then you say, okay, from now on, I'm going to allow only real numbers multiplying there. That's how we got back SU2, right? But in the intermediate step, we allowed complex numbers. Because otherwise, you cannot find eigenfunctions. You know, that was the point. Without, you know, if you had not allowed this I imaginary number here, you could not have found an eigenfunction. That was the reason. So the same thing we'll do now here. So except that now we have two independent generators inside the Cartan. So you have two eigenvalues. No? Each, you see that they simultaneously commute. And you know this theorem that if you have two Hermitian operators which commute with each other, then you can simultaneously find the eigenvalues of both of them. No? If they are not commuting, you cannot find simultaneous eigenvalues. Right? This is the reason for choosing Cartan subalgebra, to be a maximal abelian. Maximal because you want as many eigenvalues as possible, right? So to classify better. Okay, so we want to do the same thing here, and so having chosen this now, you see. So let's see what are the possible combinations. Actually, you can see already. Now the sigma plus and minus So remember, so sigma plus, let's look at sigma plus, which was sigma 1 plus I sigma 2. What is this? Okay, up to an overall number. Okay, this was 0, 0, 1, 1, 0, and sigma 2 was 0 minus I 0, and then I multiply by I here. Let me put here plus or minus both, plus or minus. So if I multiply I inside, I times minus I is 1, so this becomes 1, and I times I is minus 1. Okay? So if you choose a plus sign, then what happens? The bottom guy cancels. So for the plus sign, you find that this matrix is simply 0, 1, 0, 0. For the minus sign, on the other hand, this cancels and this adds up. Okay? So for minus sign, you have 0, 0, 1, 0. And these were the eigenfunctions. Eigenfunctions meaning that they satisfy the condition that the commutator of with sigma 3 with the sigma plus minus gives you back again sigma plus minus up to some number. So the moral of the story is that eigenfunctions were either purely upper triangular or purely lower triangular, right? I mean, upper triangular meaning this part. Okay, this is just 2 by 2 matrix. So the upper triangular is just one element here. Also here, this is lower triangular. But now we are talking about 3 by 3 matrices. Okay. So we want to again get this upper triangular form or lower triangular form. Okay. And again, so what we can do, for example, I can take lambda 1 plus I lambda 2 and lambda 1 minus I lambda 2 combinations. Right? It will do the same thing because these are the sigma 1 and sigma 2 in this block. Right? Okay. So I can choose, so let's choose lambda 1 plus lambda 2 plus I lambda 2, which will be just a 0, 1, 0, everything else 0. Okay, maybe there is a factor of 2 here, right? Okay, so let me divide like that, so that 2 disappears. And similarly, if I choose a minus sign here, it's going to be 0, 0, 0, 1, 0, 0, 0, 0, 0. If I choose a minus sign. Now take again the similar thing. So just try to do sigma 1 and identify sigma 1 and sigma 2 and do this trick. So for example, now if I look at 6 and 7. So if I take lambda 6 plus I lambda 7, because again here is sigma 1 and sigma 2 there, right? So the same thing will happen. So 1/2 lambda 6 plus I lambda 7. This will be 0, 0, 0, 0, 0, 0. No, 0, 0, 1, sorry. 1, 0, 0, 0. With the minus sign, it will be just a transpose of that. 0, 0, 0. And finally, the last combination is the remaining 2, which was lambda 4 and lambda 5. Again, the same structure. If you remove the second block, then this is sigma 2, and that is sigma 1. So the last combination is lambda 4 or lambda 4 plus I lambda 5. So in this case, this is 0, 0, 1, 0, 0, 0. And with a minus sign, this is the same as the transpose of this. Okay. So, and this will all be, this will be the eigenfunctions of the, for the adjoint action of lambda 3 and lambda 8. Okay. So let's just check that. So what are the, what do we get? Maybe I can erase this. I will use both of them. I will choose once the base is lambda 3 and lambda 8, and another time I will choose instead of lambda 8, I will choose this lambda 3 and this. Okay. I mean, just to, it doesn't, there's no difference, because if I know the lambda 3 and lambda 8 eigenvalues, then of course I know the eigenvalue of this also, right? So you can easily go. But as I said, pictures will be much nicer with the lambda 8. Okay, so what is the eigenvalue? Let's see. So I want to take the eigenvalue, take the commutator of lambda 3 with any one of these guys. So let's look at, let's look at, I mean this, by the way, let me do one thing. Instead of writing these matrices and so on all the time, let me define a matrix Eij. This is a matrix. This is not the index. This is not denoting the row and column. This is just a symbol for the matrix. Okay, and that I will define as simply a matrix which is everywhere 0 except for one element, which is the ith row and the jth column, and there it is 1. Okay, so this element is 1, and everything else 0. Everything else 0. Okay. So I'm defining this matrix. So in this notation, this matrix is, so these matrices are simply Eij. Those matrices are Eij with the two Eij with I not equal to 0, right? All these matrices that we are writing down here, they are all Eij with I not equal to j, right? So all of these matrices, so all those matrices, 1 half lambda 4 plus minus I lambda 5, 1 half lambda 1 plus minus I lambda 2, 1 half lambda 6 plus minus I lambda 7. So all of them are of the form Eij with I not equal to j. Okay. What about our say the basis? I mean, so lambda 3 itself is E11. So lambda 3 is that E11 minus E22 in this notation, right? So E11 is a matrix which has only non-zero element is 1, 1, with the entry being 1. So that takes care of this number here. And E22 is again only non-zero entry is 2, 2 element, okay, with a minus sign, so that takes care of this minus 1. And similarly, lambda 8 is now, that's a bit, this 1 over root 3 is floating around here. So 1 over root 3, and then E11 plus E22 minus 2 E22. Okay, so that's the. Okay, now why I'm using this? Because actually we will again use this notation later in the more general discussion. So this is the reason why I'm using it already. And not only that, but also you can see eigenvalues immediately. So let's suppose I look at a product Eij, EKL. Is a matrix. Each of them is a matrix, right? This is a matrix of the same square matrix. So now I'm taking the product of these two matrices. So how does it look like here? So this is this matrix has the only non-zero entry is the ith row and the jth column for the Eij, right? And that entry is 1. Everything else 0. Everything else 0. On the other hand, EKL is a matrix whose only entry, non-zero entry is the kth row and lth column. Okay, this is 1 and everything else 0. Okay. So when I do the matrix multiplication, what do? I take a row here and multiply to the column here, right? Now, the only column which is not 0 is the lth column, right? So what will happen? So anyway, so I mean, first of all, when I take the first, I mean from first row to I minus 1th row, these are all 0. So that's going to be 0 anyway, right? I mean, all of these rows are 0, 0, 0 completely. So when I multiply, no matter which one I multiply, it doesn't matter because this is 0 already, right? So we conclude that the the result of this multiplication will be that the first from 1 to I minus 1th row, everything is 0. Okay? Everything is 0 up to that point. Now look at the ith row. And the same thing happens from I plus 1 to whatever the says n by n matrix, let's say n by n matrix. So the same thing will happen from I plus 1 up to nth row. All of this will be 0. Right? All of these guys will be 0 here, and all of these are 0. That's simply because all these rows are 0, so nothing happens, right? The only possibly non-zero term can come from the ith row, because in ith row there is one element which is not 0, right? But that is going to multiply. So here is a jth column, right? So that is going to multiply the jth row here. No? But here the only row which is not 0 is the kth row. So the only way I can get, so suppose j was not equal to k. Suppose j was not equal to k. Then you see this 1 is never going to hit this row. No? When I multiply, so you remember the multiplication is you take the row and multiply to the column, right? So here we see that the only non-zero entry is in the kth row. So for it to be non-zero, this j must be equal to k. No? So what we are concluding is that, so even this would be 0, even the ith row, this ith row would be also 0 if j was not equal to k. Okay? But if j is equal to k, then it will not be 0, right? So first of all, we see that whatever the answer is, there should be a delta jk. Only if j equal to k, possibly it will be not 0. And so what is that matrix then? It will be something, so we are taking the ith row and lth column. So I'm assuming that j is equal to k. So I'm assuming that j is equal to k. Then if I take this product of this row with that column, lth column, then I would find a non-zero number, which is 1. Right? So we are saying that the only non-zero entry in that case will be, so if j equal to k, then the only non-zero entry will be the ith row and lth column. This one will be non-zero. Everything else will be 0. Okay. So we see that it is EIL, but that's the definition of EIL. EIL is a matrix whose only non-zero entry is the ith row and lth column. Okay. So this is an interesting property here. So this matrix satisfies the condition delta jk. So it's the delta of these two, delta jk times EI. Time is going fast. Okay. So now let's look at. So this is the general. That's a kind of. So now you see I don't have to write all these big matrices. I can just use a symbol. No. But is there any question on this? Is that clear? Is that just using the matrix multiplication rule? You know, you just take the row, multiply to the columns. For the row of the first matrix, so rows of the first matrix will multiply the columns of the second matrix, right? And then use the fact that this one has only non-zero entry for the ith row, jth column, and this one has only non-zero entry for kth row and lth column. So that gives you this rule. Okay. Can I erase this now? I think I can erase this, right? Yeah, I mean, so basically we concluded, right? All of these guys are, and in fact, yeah, okay. For the plus signs, the plus signs here, notice that these are all, the entries are non-zero only in the upper triangle, right? So here, for example, here is also upper triangle, and here also upper triangle. No, that means so that means this ij, j is larger than. So if for the plus sign, what was here? Was I writing here? For the plus sign, Eij with I, so with j greater than I, right? Because you see, I is the row and j is the column. So this was 1, 3 element is not 0. Here is 1, 2 element is not 0, and here 2, 3 element is not 0. So j is greater than I. And for minus sign, it's the other way around. It's a lower triangle. So in this case, Eij with I, with the j less than I. And the karta is when I is equal to j. But in some combinations, because these combinations are coming because we have a tracelessness condition. If we didn't have tracelessness condition, if we were doing U3, then there will be all independent, E11, E22, and E33. So in U3, the karta will be 3-dimensional. Not 3, but for SU2, traceless condition is giving you that. Okay, now with this, we can immediately work out all the, I don't want to erase that. Can I erase this part now? I mean, the summary of that, this computation is here. No? So I can erase that now?
Professor, I
Yeah.
have a question.
Yeah.
Here in the step 2, when we take the combination of the other 6 generators, in this combination, we don't see here lambda 6. So
We don't see what? You don't see?
lambda 6.
Sorry, this is lambda 6. This is lambda 6.
Okay.
Huh? So half lambda 6 plus or minus I lambda 7.
Yes, thank you.
Yeah, so because, yeah, this is exactly, again, the same thing. If you look at this block, this block here, this is sigma 1, that is sigma 2. No? So again, the same combination. It's always sigma 1 plus or minus I sigma 2 combinations in a 2 by 2 blocks. Okay. So now I can erase this. Okay. So now let's look at lambda 3 commuted with Eij, where I is not equal to j. So we are looking at the remaining, at these types of terms. If I was equal to j, then of course it commutes, because both are diagonal. So then of course it will commute. So the only non-zero possibility of non-zero commutation relation is when I is not equal to j. Okay. So that is the same as, because we said it's E11 minus E22. Lambda 3 is that, commuted with the Eij. And then we can just use this rule. So actually maybe I can write also the commutator. This is just a product like this. Suppose I want to look at the commutator, Eij, EKL. Commutator. So it will be Eij, EKL minus the other way around, right? So this term we already know is delta JK, EIL. Now if I look at the next other term, it will be minus. So now it's KL Ij, right? So it will be KL Ij. So delta Li, and EKJ, right? No, because the other term, you just exchange the pair Ij with KL. So if you exchange, so you exchange J with L, K with I. So this delta JK becomes delta Li, and this becomes that. So you get. So now I can directly work out. So E12, so E11 with Eij is. So use this thing. So there will be delta 1i times E1j. Okay, minus the other way around. So delta J1 times EI1. And from the minus E to 2, just replace 1 by 2. So minus delta 2I E2j minus, so plus delta j, Eij. So 1 is to be replaced by 2, Ei2. Okay. So now, so let's see if this is, so what we want to show is that this is the same as something proportional to Eij. Okay. So let's see if it works. I mean, so this, if I is not equal to 1, this is 0. No? So yeah, I mean, so let's see how to do this. Maybe better to just, so let's just take some special cases. So let's say these are the 3 cases, right? So actually we have only 3 cases. So take I, j equal to 1, 2.
Actually, the delta j2 is negative. Because of the negative sign in Q2.
Is that so? Maybe because there's a minus sign here, no?
Yeah.
You took that into account?
Oh, yeah.
Huh? So suppose that I and j is equal to 1, 2. So let's look at E1, 2. Huh? So which is this one? This one is a E1. That's E1, 2. This is, no, E1, sorry, E1, 3. This is E1, 2. And that is E2. These are the 3 things. We are looking at this case where I is greater, j is, sorry, the plus sign. So j is greater than I. So if I and j are 1, 2, which means this one, so what do we get here? So I is 1, so this becomes, this is now 0, and you get here E1, 2, right? Because j is 2. And here j is 2, so that vanishes. Okay? So this delta 2, 1 is vanishing. Here 2, 1 again vanishes. And what you get here, j equal to 2. So I is 1, so it's 2 E1, 2. Right? And same thing you can do also for, let's say, if I take 1, 3. If I look at E1, 3, so E1, 3, with this, so if I look at, so the first term gives you E1, 3, right? I is 1 and j is 3. This one is vanishing. And here, this also vanishes. And that gives you, that also vanishes, right? So everything vanishes. So just E1, 3. So this one is a coefficient 1 times E1, 3 for E1, 3. And finally, what is left over? E2, 3. E2, 3 again. So this vanishes. I is equal to 1. So I equal to 2 will survive here, which is minus E3. Okay. And so what we see conclude, I mean, maybe I can erase this, one of these, let's see, erase this. So we are seeing that lambda 3 commuted with E1, 2 is, I can just write down 2 E1, 2. Lambda 3 with E1, 3 is, lambda 3 with E1, 3 is, we said 1 E1, 3. And lambda 3 with E2, 3 is minus E2, 3. Okay, I hope I have not made any mistake. Okay, what happens if I exchange j and I? No? So we are looking at, so now we are looking at a situation where, or we're not, so this was for this one, right? Now we look at the bottom triangle. So in that case, j is less than I. Okay. So if j is less than I, then we can have E21, we can have E31, or we can have E32. These are the 3 possibilities, right? If I is greater than j, which means a lower triangle, which means this one, and this one. Okay. Lower triangle. For the minus signs, for the choice of minus signs here. So again, let's do it one by one. So if I take E21, so I is 2. So I is 2, this of course drops out. That will give you a minus. And then E2, and j is 1. So j j is 1 here, so that's that. What about here? You get here again, so j equal to 1, this survives, but that doesn't survive, that vanishes. So you get here again a minus sign, and you again get 2, 1. So a factor of minus 2. Okay. So we conclude here that lambda 3 with E21 is minus 2E21. And you can check all of them that the sign just changes. So lambda 3 with E31 should be minus E31. And finally, lambda 3 with E32 is, this was minus, so minus of that is plus E32. That is so as far as lambda 3 is concerned. Okay, now let's look at lambda 8 combinations. Is that, do you want, you want to check this results? Actually, already from here you can probably see that if suppose I is equal to j, so if you look at I with KL, so this is, because for the one side it's always diagonal, right? This is diagonal, all of them are diagonal. So delta jk and delta, so both are I, so ik, delta ik, delta il. And if you exchange k and l, I think you should be able to see that this sign, this exchanges, and I think you should be able to see that the sign changes. But although, even if you don't want to do that, you can just directly look at this and get the same result. Okay, this is that. Now, what about lambda 8? Okay. So let me also do this here. 8. So you want to look at E11 plus E22 minus 2E33. Now there are a lot of terms here with say Eij. You want to look at that, and there is a 1 over root 3. I have to put 1 over root 3 in there. So I'll keep this 1 over root 3 for the time being out. So if I just plug that in here with the same formula, this formula here, with the E11 with the Eij will be so 1 1. So it's delta. This is the same thing. Yeah? Delta 1i E1j minus delta j1 ei1, and with the 2 2. Here was a minus, but there's a plus sign, so we just have to flip the signs of these two. So plus delta 2i E2j minus delta j2 ei2, and then minus 2 E33. So from this one result, I just have to replace 1 by 3. No? So you get here, but there's a factor of minus 2. So minus 2, I have to replace 1 by 3. So delta 3i E3j and minus plus 2 delta j3 ei3. Now, this is a bit of a mess to check each one of them. So if I take again E12, so I is 1, so this drops out and that drops out, so only that survives here. So you get here E12, and here J is 2, so this drops out, only that survives. So so it cancels, it's 0. So maybe I should write it here somewhere. Right here. So lambda 8 with E12 is 0. Okay. Then look at 1, 3. Let's say 1, 3. So 1, 3. So when I equal to 1, this survives, so that's E13. And nothing else survives here. Here, j is equal to 3, so only this survives. So you get here plus 2 E13. So plus 2 E13. So 3 E13. So lambda 8 with the E13 is 3 E13. But I have to also remember the 1 over root 3 factor. In the lambda 8, there was a 1 over root 3. So I put here 1 over root 3. And then, finally, we have E23. So from delta 2i, this survives. So you get an E23 from here. Nothing else. And then from here, j equal to 3. That survives here, right? Which is again plus 2. So 3 to 3 again. So lambda 8 into 3 equal to same thing. So 1 over root 3, 3 equal to 3. Yeah. And once again, the other guys will be, so lambda 8 e to 1 is 0, lambda 8 E31 should be minus root 3 E31 and lambda 8 with E32 is equal to the minus root 3. No, I mean, let's just check this. So it's, for example, if I take this 3-1, if I take this 3-1, just to see the sign, flipping of the sign, E31. So I is equal to 3, this survives. So you have the minus 2 from here. E31, it will be always E31. E31. And if for j, this is j equal to 1, so only that survives. So you get here minus 1, minus 3. Minus 3 over root 3, so minus 3. So this is the structure. This is the, so we have been able to simultaneously diagonalize. I mean, this is nothing else but the add, right? This is by definition add lambda 3 acting on E12. All of these things are add. So this is it by definition add lambda 3 acting on E12. And this is for E13 and so on. And these are all add lambda 8 acting on that. So these are the eigenvalues of the adjoint representation. Adjoint representation of lambda 3 and lambda 8. I mean, each of these thing is some operator. This is a since it's a add is a 8-dimensional Lie algebra. This will be 8 by 8 matrices. No? If you view it, if you think of acting on the Lie algebra itself, it's 8-dimensional. So this is acting on an 8-dimensional vector space, and it is giving you the rules now. This is telling you that. We have all of them are eigenfunctions. So add lambda 3 and add lambda 8 are diagonal in 8-dimensional representation. Right? As an 8 by 8 matrix, it will be diagonal. But what we can do now is to try to draw a picture of the eigenvalues. Remember, for SU2 we drew a picture. There was only one quantum number, which was the what were we calling it? Sigma 3. No, we were calling it, what were we calling? H. I think we were calling H, right? A capital H or something like that. No? So it had only the highest weight state, which had some spin j, and H eigenvalue j. And then you had a j minus 1, j minus 2, all the way up to minus 2. Right? So these are in this diagram, what I was plotting was the eigenvalues of the H, no? In whatever representation you're talking about. No? In the adjoint representation, if you look at the add H, which is a particular representation of the SU2, right? In that case, it was simply the spin was just j was equal to 1, so you had a plus 1, 0, 0, and minus 1. But this could be you could plot it in one dimension because there was only one eigenvalue. But now we have two eigenvalues. Eigenvalues with respect to add lambda 3 and eigenvalues with respect to add lambda 8. So so you can plot it in two dimensions because you have two numbers. No? Each state, each of them, say E1, 2 has an eigenvalue with respect to lambda 3, which is here 2, is a 2 here, and with respect to lambda 8, it is 0. No? But look at E1, 3, it has one eigenvalue 1 with respect to lambda 3, whereas with respect to lambda 8 is root 3. No? So let's plot. So what we'll do now is to plot so on this axis I plot lambda 3 eigenvalues, or more precisely add lambda 3 eigenvalues. And in this direction I plot add lambda 8 eigenvalues. So so here so we find let's do for each of them. So E1, 2. So what are the eigenvalues of E1, 2? So E1, 2 eigenvalue are 2 and 0. So this is the eigenvalue with respect to add lambda 3, and this is the first entry. The second entry is the eigenvalue with respect to lambda 8. So 2, 0. So that would be 2 here. So I don't know, let's plot it. So 1, suppose this is 1, that's 2, 2. And then we have to go to 0, so that's 1 point. Okay. So that is the E1, 2. So I'll put here, on this spot, I put here E1, 2 to indicate that E1, 2 has this eigenvalue. So this means E1, 2 has eigenvalue 2 with respect to lambda 3 and 0 with respect to lambda 8. Now let's look at E1, so E1, 2 we did. E1, 3. So E1, 3 is 1, comma root 3. Right? The lambda 8 eigenvalue is is root 3. 3 over root 3 is root 3. Let me just write it like that, root 3. Also this is root 3. So 1 comma root 3. So you try to plot that 1 comma root 3. So root 3, so if I draw it, it's difficult to, what is root 3? So root 3 is somewhere between 1 and 2, right? Actually closer to, so something like this here. Something like this. So this is E1, 3. Actually, you can see, we are saying that this length is root 3 and that length is 1. So tan, if I try to look at this angle, theta, so tangent tan of theta is root 3. But that happens for 60 degrees, right? So this theta is 60 degrees. Okay. So this angle is 60 degrees. Okay. Now let's look at the what is left over, E2, 3. So that is minus 1 and root 3 again. So it's just a mirror image. If you look at the mirror image, so this is minus 1, but this is the same. So I don't know, somewhere here. And this angle is also 60 degrees because this is again root 3 here, 60 degrees. So therefore this angle is also 60 degrees. Okay, and then for the other 3, it is just a minus. Both the eigenvalues are minus of the original eigenvalues, right? So it will be just diametrically opposite. So this will be, if you extend the line, it will be somewhere here. This guy will be somewhere here, and this guy will be somewhere here. Okay. Second thing you notice, this is 1 and root 3. So what is the length of this? Because it's Pythagoras theorem, use Pythagoras theorem. So 1 plus 3, which is 4, square root of 4 is 2. So this length is also 2. Okay. Just like this one, this length is 2. Okay. All the lengths are 2. Okay. And all the angles are 60 degrees, everything. So it's a perfect hexagon. We just join these things here. This is a hexagon. Okay. this is what is called, these eigenvalues are called the roots. Roots. I mean, I will make the more precise definition. But let's say here I'm writing down the roots in this choice. I have chosen a particular basis, lambda 3 and lambda 8. No? In this basis, it comes out as a beautiful hexagon, I mean regular hexagon. No? If I had chosen a different basis, not lambda 8, but say that other combination which we are using, lambda 8 minus root 3 lambda 8 minus lambda 1 and so on and so forth. In that case, the picture will not be like this. Okay? If you are, instead of plotting lambda 8 eigenvalue, if you are plotting root 3 lambda 8 minus lambda 1, lambda 3 over 2, no? Then it will not look like this. The fact that it comes out perfect hexagon here is because Gell-Mann basis satisfies this condition, right? Trace of lambda A, lambda B is proportional to delta A. That's the reason why it comes out like that. If you had chosen some different basis, it would not be, in general, looking so nice. Now, if you now look at this picture here, of course, I mean, I can add to this also this here, no? I can also add to this that add lambda 3, acting on lambda 3 is of course 0, right? Because lambda 3 commutes with lambda 3. And the same thing with add lambda 3 acting on lambda 8 is also 0. Both are diagonal matrices, so the commutator is 0. And the same thing add lambda 8 acting on lambda 3 is 0, and add lambda 8 acting on lambda 8 is 0. Okay? So really at this point 0, so in other words, eigenvalue of lambda 3 and lambda 8 is 0 each, 0, 0, right? So eigenvalue of lambda 3 is, is 0 with respect to that and 0 with respect to that, the same thing. So those are the 2 points here at the origin. Okay. So that's the picture which is writing. Okay. Now, this picture has also many other things you can read from this picture actually. Now what can I erase here? Okay, I think I can erase. Maybe some formula I should keep that. You don't want to derive this formula again. Okay. So this is fine. So what we have done basically is at the moment, we have taken all the commutation relations of all the generators, but only with lambda 3 and lambda 8. We have still other commutators, right? Commutators of this E12 with E13, or those things we have not checked yet. We have not looked at it yet. But because we were only interested at the moment for the eigenvalues, and these are the eigenvalues here. Now, so one can ask the following question. So our next step is to find the commutation relation between Eij and Ek-L, which was already given here, right? But for those where I is not equal to j and k is not equal to l, right? So those are the remaining ones which we want to check. But now, whatever it is going to be again in the Lie algebra. So it is going to be again some linear combination of all of these guys, right? But one can ask the question: is it also an eigenstate? Eigenstate of add lambda 3 and add lambda 8 simultaneously. Right? So we want to ask whether this is an eigenstate. Is it an eigenstate of? I mean, surely it belongs. It is contained in the SU3. So it is going to be linear combination of all the 8 generators, right? But we are asking a further question. We are saying we know that these guys are eigenstates of add lambda 3 and add lambda 8. That is the content of this. No? These are all actions of add lambda 3 and add lambda 8. So add lambda 3 on E13 gives you back again E13 times some number. No? So in that sense, these are all eigenfunctions, no? Of add lambda 3 and add lambda 8. Now we are asking the following question. If I take the commutator of these two, is it again eigenfunction of lambda 3 and lambda 8? Add lambda 3 and add lambda 8. Right? And if so, what are the eigenvalues? Can we say something about it? So let's look at add lambda 3 or lambda 8 acting on now this commutator Eij EKL. Okay. But that's the same, by definition is the same as the commutator of lambda 3 or lambda 8 with Eij EKL commutator. Okay. But now use the, okay, I don't want to erase that diagram. Maybe I can erase this because we don't need now a very precise form, right? Anyway, that is in the notes, so you can. Okay, so now we use the Jacobi identity for the triple commutator, no? Identity. Basically, that identity can be written in this way, and I think writing in this way it's easier to remember. Okay, so if I write it like this: x, y, z. Okay, then this Jacobi identity implies. So this implies that this is the same as x, y with z plus y, x, z. You can check that. You can see the usual Jacobi identity. You think in terms of a cyclic thing, right? But that is the same as this. The reason why this is easier to remember, at least I find it easier to remember, is this is as if, this action is like a derivative. No? So we have two terms here. So if you think of this as a derivative, then if you use the Leibnitz rule, no? It's like taking first the derivative of first guy, which is this, right? xy, and then the derivative of that. Okay? In fact, this analogy is not, mathematicians in fact call this as a derivative. This action as a derivative. No? So it's, but it's easier to remember. Now if you do that, if you use that, so what we are saying, so let's do this lambda 3 Eij. But please check that the cyclic, the standard Jacobi identity implies this. Okay? The content of this equation and the Jacobi identity is identical. There's no difference. It's the same content. So Eij EKL is the same as the commutator of first lambda 3 acts on that. So lambda 3 Eij with now EKL plus the second term where Eij remains there and lambda 3 EKL. Okay. But that's great because this we already know this is an eigenfunction, right? So this is going to be some number times Eij. No? But then what is left over is that number times the commutator. That number is the eigenvalue, right? So let me just write it like this. So this quantity is the, what shall I call it? The eigenvalue of Eij. I don't know, some number, let's define some notation. Xij, let's say, 3. To indicate that it is eigenvalue with respect to the lambda 3 and not lambda 8. Of Eij. This is a number. Which are these numbers? 2, 0, all these numbers. Xij, Eij. This the commutator gives you that. And then I still have to do this commutator. So EKL. That's that. And this one will be, again, the eigenvalue x3 of KL, EKL. And so this number I can take it out. This number is just a number. I can take it out. And what is left over is Eij, EKL. Both are the same. Both are the same states as the original state, original object we are looking at. Right? This was the, by definition, add lambda 3 acting on this Eij, EKL. So we see the first conclusion is that indeed this is again an eigenstate because we are seeing that every term is proportional to that. Both the terms are proportional to the same thing, right? So this is again, so answer is that this is an eigenstate. So these guys are eigenstates. That's the first statement. of add lambda 3 as well as add lambda 8, because you just have to replace lambda 3 by lambda 8. Same argument goes through. No? It will be just this eigenvalue will be replaced by x8. So I can add eigenstate of lambda 3 and add lambda 8. But moreover, we have more information. We are also finding out the precise eigenvalue. It is just the, once you take this out, what is the number multiplying? Xij3 plus xkl3. But xij3 is the eigenvalue of this, Eij, and that is the eigenvalue of ekl. So what we are saying, and the result, and the eigenvalue is the sum of two eigenvalues, of the eigenvalue of Eij and ekl. So it's additive. You just add. No? Eigenvalues you just add up. Okay? And that happens both for lambda 3 and lambda 8. That means as vectors you can add. Because this vector has information of lambda 3 eigenvalue and lambda 8 eigenvalue. But each of them are adding up. No? So this is a vector sum. So the root for the Eij, so I just have to take the vector for the root for the Eij. These are the roots. No? And root for the ekl and add them up. Vector addition. No? Okay. So now we can immediately see what, from here we can see what is happening. So if I take, for example, if I take the commutator of E12 and E13 and E12, okay, the right hand side should be again, it should be, it should have an eigen, it should be something whose eigenvalue will be the sum of these two roots. But the sum of these two roots do not exist. I mean, this was the set of all roots, right? All the non-zero roots we have drawn. I mean, we have taken into account all the 6 remaining generators outside the Karka. If I take the sum of these two vectors, okay, it will be the parallelogram, to draw a parallelogram, then this will be a vector, right? But this doesn't exist. So this concludes that E12 with E13 must be 0. And you can check it. I mean, we have this, you can just, the first term was a product like this times that, no? E12 with E13, because then you can check that by using this formula, that it should vanish. Okay. What about, let's look at the commutator of E12 with, what was this? This was, did I write? This was E13, this was E32, right? No, this was E23, no? Yeah, this was E23. I just erased it. This was E23. And then the other ones were, so this was E21, this was E31, and this was E32. I mean, meaning what this notation means that this is the eigenvector corresponding to E12, and so on and so forth. Okay, so this is 0. What about E12 with E23? Well, it's whatever it is, its eigenvalue should be the sum of these two vectors. So I have this vector and that vector. This picture is not very good, right? Because this length looks to me bigger than that length. No. So it's not, the picture is not, but just imagine, okay, maybe I can make it smaller. So this, it's something like here, this length. Okay. This should be the midpoint of this, right? This is an equilateral triangle, actually. And this should be the midpoint. So if I take the sum of these two, if I draw the parallelogram, it is going to be, you see this is 60 degrees, so this is going to be 60 degrees. So it will exactly be this line, this point. So then this will be proportional to, has to be proportional to E13, right? Because we are saying that if this eigenvector of this is actually this one, but we know this eigenvector for the E13. Okay? So it must be proportional to E13, some number times E13.
But this number can't exceed exceeds 1, right?
Can what?
Can't exceed 1. It has to be a fraction, right?
It could be any number actually. I mean, it depends very much on your even the normalization of E12 and E13, etc. No? You may choose different normalization. Here we have chosen a very specific choice, no? But there is no risk. Given an eigenvector, I mean, given say E12, I can just multiply by any number. That will still be an eigenvector. No? So this number doesn't have too much of importance. The main thing is whether it is 0 or not 0. No? So this is not 0. Okay, this we have not proven that this is not 0. This coefficient is not 0, right? I mean, here we proved that it has to be 0 because there is no such thing. There was no root like that, no? Here we have a root here. There is a possible root. So it could be, it's going to be some number, x times E13, let's say. But that x might be 0. That one has to check. Okay? In fact, we will prove in a general, you should actually try to do that. Try to check this. In fact, we can check it directly from here, right? So we put 1, 2, no. What is going on? Is it correct, this E23? Yeah, it's E23. So 1, 2, 2, 3, right? If you look at this, put the 1, 2 here and 2, 3. So delta jk, this term is not 0, no? So you get here 1, 3. So indeed you get 1, 3. So it's not 0. In fact, we'll prove when we discuss general algebra that whenever the roots of these two, the sum of these two roots exists, is one of the allowed roots, then this is not 0. Okay? So commutator is not 0. That one can prove in general. But okay, here we can do explicitly. This is one thing. And then similarly you can do, for example, let's say this with that. So E12 with E31. This with that. If you add the two vectors, you're going to get that vector. So you'll get E32. And so on. I mean, just from this picture you can immediately guess. Huh? Finally, what happens, I mean, this was, so we were looking at so far, say E12 with all the others, but not with the E21, right? Now what happens when I look at the commutator of E12 with E21? Well, it's again, this vector plus that vector is actually 0 vector. Okay, so what is 0 vector? 0 vector is the 0 eigenvalues for both lambda 3 and lambda 8. Then those are the Katha subalgebra elements, right? So therefore we are concluding that the commutator of E12 with E21 should be some combination, let's say x1 lambda 3 plus x2 lambda 8. Some combination. Actually, in this particular case, you will see that it is just lambda 3. I mean, it is, because that was an SU2 subalgebra, remember? I mean, E12 was 0, 1, 0, 0, everything else 0. Right? This was E12. E21, on the other hand, was a transpose of that, 0, 0, 1, 0, 0. Right? So, if, and lambda 3 is again the top block. No? So, for these commutators, you can just ignore this third row and third line, column. No? Then it is just a sigma plus, what we call sigma plus, sigma 1 plus I, plus or minus I sigma 2, up to some overall number. Okay? This is proportional to sigma plus, that's proportional to sigma minus, and this is sigma 3. No? And the commutator of sigma plus and sigma minus gave you some number times sigma 3. So this is going to be some number times lambda 3. If you take the commutator of E13 with E31, then you will see that you will get both of them, lambda 3. So if I take now E13 with E13 with E31, so this with this, then you will get a combination of lambda 3 and lambda 8. Okay, but that combination will be exactly, the relative coefficient will be exactly related to this angle. Okay, I mean, try to work it out, and you'll see that it's going to be some combination involving involving this angle 60. So maybe cos 60, sin 60, something like that. Huh? You try to do that. Huh? And same thing with the E23 with E32. Okay. So this is the general structure of the algebra. This statement, this theorem is, I mean, this result is very, very, very strong result. This result is very strong. That, I mean, the final conclusion was that, no? That the commutators just give you again, I mean, just the root vectors add up. When you look at the commutator, root vectors add up. Very, very strong result actually. And so from that, you can just by staring at this picture, you can immediately see what vanishes, what does not vanish, etc. No? And there are SU2 subalgebras. So what happens here? So let's say, so these are the three SU2 subalgebras I was mentioning. I think somebody asked the question, how many SU2 subalgebras are there, right? For every root, for every non-zero root, there is an SU2 subalgebra. Let's say, maybe let me use some terminology. I will call, I mean, you see here in this picture, it's only one dimensional. You could talk about positive and negative, right? So these are the positive eigenvalues, those are negative eigenvalues. When you're in two dimensional, it's not so clear how you should define your positive or negative. So the way you usually do, I mean, that's completely, there's no rule for that. I mean, you can just choose whatever you want to call positive. But you have to do it in a way that you have to choose some line in this plane, okay, which does not, which is not kind of, I mean, don't choose this line. I mean, because this line already has the roots, no? So choose some line which is not passing through the roots. So for example, this line, or for example, this line, any line, choose, okay? And then just you declare that everything lying on one side of this line, I will call them positive root. Everything lying on the other side of the line, I will call them negative root. Okay, that's you can choose whatever your definition. The things will not change. Okay? So if I had chosen this line, this is my line, then positive roots are the ones, these three are positive roots, and these three are negative roots. Okay. So positive, when I say this, so that means the lambda 3 eigenvalue is positive, right? Because this direction is lambda 3 eigenvalue. No? On the other hand, if I had chosen this line, then these three are positive roots. Okay. In that case, some particular combination of lambda 3 and lambda 8 eigenvalue should be positive. No? But you should not choose, for example, this line, because then this line is passing through the root. No? That is not valid, because then you don't know whether you should call these guys positive or negative. No? You can say this is positive or that is negative, but it's ambiguous. So to be unambiguous, you should choose a line which does not pass through the roots. And then you can define. But the upshot, no matter what you choose as you're defining positive or negative, the statement is that for a given positive root, there is always a negative root, which is exactly the negative of that root vector. Okay? This is the completely general thing. This happens for every Lie algebra, not just for SU3. And that is very important, because what this will say is that if you take, so this lambda 3 and lambda 8, these are already, the commutator of that with E12 gives you back E12. Also with E21, it gives you back E21. But commutator of E12 and E21 gives you back a particular combination. Actually, in this case, purely lambda 3. Right? That means there's an SU2 subalgebra. Right? SU2 subalgebra where, say, call this as sigma plus, that as sigma minus, and that particular combination which enters in the commutator, call that as sigma 3. No? That's an SU2 subalgebra. Same thing with this. If you take this guy, this, and another combination, that particular combination which appears here, that will form another SU2 subalgebra. And this will also form another SU2 subalgebra. Okay? So for every positive root, or equivalently every negative root, there is an SU2 subalgebra. That is the that's the general, that's the structure we are seeing in SU3. But of course, it's a very complicated structure. It's not, I mean, unlike SU2, so say this SU2 and that SU2 are not, they don't commute with each other. No? For example, if you look at this SU2 and that SU2, this is the sigma plus for this SU2, right? That is sigma plus prime, let's say, for the second SU2. sigma plus and sigma plus prime don't commute. Because we saw that this commutator gives you that. No? So it is kind of rather complicated, but nevertheless there are SU2 subalgebras, several different SU2 subalgebras. But they just don't commute with each other. That is the point. Yeah. Okay. So yeah, really you think of, say, the positive roots as raising operators, no, and negative roots as lowering operators. And okay, just one final comment. Then I have to continue. SU2 is not finished yet. Tomorrow we'll continue with this. But just one more comment. Just like this here, there is a. I mean, this was all we are discussing about the adjoint representation, right? These are all adjoint representation. We are working in the this add. But what happens in some other representation? Okay. So let's suppose I look at some other representation. So some arbitrary representation R. Some arbitrary representation. And then again, look at, we can again look at, any state, we can again look at R lambda 3 and R lambda 8 and diagonalize them. No? We can find the eigenvalue. We can write all the, in any representation, we can write, for example, take the three-dimensional representation. Three-dimensional representation was the defining representation. All the things were defined as 3 by 3 matrices. Lambda 3 and lambda 8 were already diagonal. So that was already diagonal. No? But you can do it for any representation. You can just find the eigenvalues with respect to lambda 3 and lambda 8, simultaneous eigenvalues. And so there will be some state, let's say some state psi, which has some eigenvalue with respect to lambda 3, let's say W1, or call it W3 psi. And with respect to the lambda 8, it has some number W8 psi, right? So once again, you can draw this W3 and W8 in that diagram, right? It will not be this point, it will be some other point. No? W3 will be along this axis and W8 will be along that axis. You can draw in this diagram. But what is the use of that diagram is that, now suppose you start applying the creation or annihilation operators. I mean, this raising or lowering operators. So I want to ask the question, if I apply any one of them, let's say RE12, active psi. So you ask the question again, is it again simultaneous eigenfunction of both? No? And if so, what is its value? What are the eigenvalues? No? So let's check that. So let's look at R lambda 3. So we want to ask the question, is it an eigenfunction? Which means, is it again some number times that? No? So the standard trick we use always, no? Because we don't know, we know how it acts on psi from this equation, right? So what you want to do is to try to push it there. But in pushing, what you do is you use a commutator, right? So I write this as a commutator, R lambda 3, R lambda 8, RE12, commutator, active on psi, plus now R lambda 3 is there, RE12, R lambda 3, active on psi. Okay, right? This is the same as R lambda 3, RE12 minus RE12, R lambda 3. So that minus term cancels with that. So this is the same as that. Now we know both of them. We know that this R lambda 3 E12 is the commutator. So this is the same as R by the fact that the representation preserves the commutation relation, is the same as R of the commutator of lambda 3 with the E12. No? This guy. But this, on the other hand, you already know, this is nothing else but the eigenvalue of the 1, 2, which was 2, I think, right? So whatever it is, some eigenvalue, let me call it again, right, it's x1, 2, 3. x1, 2 meaning of the E1 eigenvalue, and 3 meaning with respect to lambda 3, times E1, 2. Right? So therefore, this is a number, and remember, representation also preserves the vector space structure. So number I can take out. So this is the same as x1, 2, 3 times E1, 2, R1, 2. So therefore, the first term is RE12 active on psi times x1, 2, 3. Okay. Is that clear? Any question? No. Okay. Second term, R lambda 3, we say is W3 here, right? So this guy just gives me R lambda 3 active on psi, use this formula here. This is simply W3 at times psi. So W3 is the number, again I take it out. So this whole thing is x1, 2, 3 plus lambda 3. Okay, lambda 3. Okay, maybe to keep this same convention, I should put here 3 up 8, because here I put that thing. So W3, this is W3 times R1, R of E1 to psi. So what is the conclusion then? This is in fact an eigenstate again, right? Because when this acts, this is a number times that, right? It's just that this eigenvalue has changed. Initial eigenvalue is W3, but now it is added to that this x1, 2, 3. Okay? Same thing you do for lambda 8. The result will be the same, except that this will be replaced by, this will be finally replaced by x8, 1, 2 plus W3. Plus W8. Sorry. 3 will be replaced by 8. Times again. Yes. So we see that this combination, I mean this RE12 acting on that, is a simultaneous eigenfunction of both R lambda 8 and R lambda 3. Right? And moreover, we also know what the eigenvalues are. They just add to the original eigenvalues. These eigenvalues, the roots, these are the roots of the E12, right? Which means, again, it's a vector sum. If you draw this W3 and W8, again, as some point, for example, let's suppose W3, W8 was some point here, W8 in this picture, then when RE12 acts on that state, the result will be again another state where you just add this vector to that. So this kind of diagrammatic, I mean, it simplifies a lot, when you try to study how the things act on in various representations. Okay, maybe I'll just stop here now, and then we'll continue more. I mean, there are many more things to say about SU3. Hopefully by tomorrow I will complete SU3. This was that's why Gelman was calling this an octet way. I mean, this is 8, no? The 8 dimension. But so he put pi plus here, pi 0 here, pi minus here, k plus, k0, and there's another k0 bar, k minus, and then there was an eta. Though that formed 8 mesons, octet. Any questions?
One small question. The two coefficients they are not necessarily the same. So
sorry, repeat again.
x12 and x123 and x128.
Yeah, I mean for E12, x123 was just this 2, right? This number 2, and and this number was 0. I mean, so yeah, in that case, this is 0 and that is 2. if you had chosen not 1, 2, but say 1, 3, for example, in that case this will be x3, 1, 3, x8, 1, 3. So in that case, this will be root 3. I mean, this will be 1 and that will be root 3. No?
What was 5, 0?
What was?
What was 5, 0 for?
Please repeat again.
I think it was 5, 0 for.
You, sorry, what?
Like you said that's 5 plus and then 5, 0 and 4 minus.
No, this was, as I said, I mean, this, I mean, that is the Gelman's original motivation. You're asking about the Gelman's thing, right? Yeah, it's, I mean, there were these mesons. I think you will study all these, no, probably not the Gelman's optic because that's very old. But you will study all these mesons and so on in the particle physics course. I'm sure they'll be discussing all the stuff. But, I mean, in the old times, much before, I think, the quark theory, before the quarks were really even known to exist. I mean, people knew already only the pi mesons, well, several mesons, but and then k mesons and some eta mesons. Okay? So the pi comes in 3 varieties: pi plus, pi minus, and pi 0. This refers to the charge, electric charge. 1 unit of positive charge, 1 unit of negative charge, and 0 charge. And here again, k plus, k minus, and then there are 2 neutral, k0 and k0 bar. And then there were several etas actually, but one particular eta combines. This is 0 charge. So I mean, Gelman tried to. These are clearly not the same. I mean, they're all pseudoscalars. They're all pseudoscalars. Scalars, meaning okay, they're not spinors or vectors or something. They're scalars. They transform under the Lorentz transformation as scalars. But pseudo just means under parity transformation it picks up the minus sign. No? So it's anyway. So they all have similar properties. They all had many properties which are similar, right? But not, of course, everything, because the masses of the k mesons were not the same as pi mesons. The masses were different. This was slightly heavier than pi mesons, and also this was a bit heavier and so on. So clearly, there is not a symmetry, no, not an exact symmetry. So what he thought, Gelman thought, was that okay, let us ignore to the first approximation the mass differences, the fact that there are mass differences. Let's ignore that and then ask the question: could there be an SU3 symmetry? You see, because if there's an SU3 symmetry, it's very useful because various interactions that this k, pi, etc. take part in, they should be governed by the SU3 symmetry. SU3 symmetry will impose a lot of conditions on that, and that you could check in your experiments, in the labs and so on. You can check whether those are true or not. Of course, nobody expected it to be an exact symmetry because there are mass differences. But okay, to the 0th order approximation, can we say that? So from that point of view, he thought that this is the joint representation of SU3, and SU3 transforms them. Okay. And he put in this hexagon, he put, this state, this what we call E12. This is also a joint representation. E12 was like pi plus, then pi minus, and pi 0. Pi 0 is like the lambda 3. And then here he put k plus, one of these k zeros, I don't remember which one, and k0 bar, and k minus. And then there was an eta here. This is neutral again, eta 0.
So the thought was if pi positive and the k node interact, they will result in this, as in the vector summation in here?
No, I mean, so, okay, now this is a representation, right? So, SU3, add SU3 will act on these states. So this will be 8 column vectors, where all possible, so you can say, for example, this guy is k plus and so on. And this adjoint representation will transform them. Right? So which means, what does it mean? I mean, if I have some state, let's say, some interaction, pi plus with pi minus going into something, okay. Then you can maybe make some transformation and take, pi plus can be replaced by k plus, right? By applying by applying what I was calling E23. If I apply E23, then this will go there. No? So then that means that if the theory is symmetric under SU3, then this amplitude should be related to some other amplitude where maybe this pi plus is replaced by k plus. You know? So these amplitudes, the probabilities, the scattering probabilities and so on, of these different processes would be related. Symmetry will tell you that they are related. And that is something you could go and check in the laboratory. But nowadays when we talk about SU3, it's a totally different SU3. What we are talking about is the strong interaction. And so that is what is believed to be responsible for quark confinements. The fact that you cannot see a free quark. You know? So quarks are so strongly interacting because of this SU3 interactions that they are always bound. You simply cannot separate them. So they are bound into mesons or baryon, protons, neutrons, no? All that stuff. So nowadays when people talk about SU3, it's a different SU3, not again that's SU3. Of course, on top of what people talk about now, there are also by the way, these symmetries are called flavor symmetries. Flavor symmetries. Because the different species of particles are being exchanged, no? These flavor symmetries. Okay. And the other thing, the strong interaction itself is called a color symmetry. Although, of course, there's no color. Because color is a concept of electromagnetism, the photons are coming interacting with the eye and so on. But for some reason, historically, they call it color. To distinguish it from flavor symmetry. Color symmetry. Yeah. That's still a very challenging thing.
Is there also an audio symmetry?
What symmetry? What symmetry?
An audio symmetry.
Audio symmetry. Sound symmetry. Yeah. No, SU3 is very, very interesting, and still some of the questions are not solved really. I mean, like the question of confinement. Confinement, everyone believes there is a confinement, and all the indications are that this confinement is there. But to really prove it analytically, it's very difficult. And people use computers, huge supercomputers to calculate it. But it would be very nice to get some analytic proof. Maybe one of you will do it. Okay, so I'll stop now and see you tomorrow. Okay, bye-bye.